As the built environment continues to grow laterally, the negative impacts caused by impervious building materials continue to increase. Shown here is Parkerson Mill Creek. This free-flowing creek flows through the center of Auburn University's campus. In order to protect Parkerson Mill Creek, special design and construction regulations have been implemented by Auburn University to reduce the negative impacts to Parkerson Mill Creek. Studies conducted in Auburn University's Green Infrastructure Lab evaluate the thermal properties of pervious concrete as it is compared to impervious concrete, commonly used in the built environment. This study also evaluates pervious concrete thickness. 4-inch and 6-inch pervious concrete test cells were evaluated to see if varying pervious concrete thickness would change its ability to mitigate heat from urban stormwater. Heat lamps were used in this study to represent the thermal load brought on by sunlight in a natural setting. 4 waterproof infrared heaters were installed above the center of each test cell rack. This offered an even distribution of heat among the 12 test cells studied in this research. Heating cycles pertaining to this study lasted for 5 hours. A 5-hour heating cycle allowed for a constant distribution of heat among the 12 test cells. Sprinklers used in this study would simulate rain in efforts to replicate a summertime thunderstorm on a sidewalk in Auburn, Alabama. 4 plastic rotary nozzle spray heads were affixed to the 4 corners of the testing area. A precipitation rate study was conducted and determined that the precipitation rate of this testing area was 0.78 inches per an hour, with a distribution uniformity of 69%. Rock test temperature sensors placed on the surface of pervious concrete 4-inch test cells and pervious concrete 6-inch test cells show that pervious concrete is actually warmer on the surface than impervious concrete. This is due to the pores on pervious concrete and their ability to trap and hold heat in their voids. When comparing leachate water and pervious concrete, 4-inch pervious test cells had a slightly higher leachate temperature than 6-inch pervious concrete test cells. This is due to the 4-inch pervious concrete having slightly less volume of concrete and a higher internal temperature. Outflow sensors placed in the pervious 6-inch concrete test cells and the pervious 4-inch concrete test cells show that infiltration rate plays a key role in leachate water temperature change. Pervious concrete test cells with a lower infiltration rate had a increased or a constant change in temperature in the leachate water. Pervious concrete test cells with a higher infiltration rate had a decrease in temperature in leachate water. The results of this study show that pervious concrete surfaces do react different to thermal loads than impervious concrete.